morning, everyone. So today we are not going to talk about linear programming. We will see how today's topic is connected to linear programming, probably either in the very end of today's lecture or beginning of next lecture. Maybe we'll devote the whole next lecture to the connection. Today we'll start talking about game theory, and in this course we'll only start talking about it, which means we'll only discuss the kind of simplest, the most established part of game theory, something which is solved completely, and unlike the illustration that I showed there, it won't be about such kind of games. It will be about zero-sum two-person games. So I have run two persons, and tic-tac-toe is maybe not the best example of zero-sum two-person game. So we'll discuss what kind of games we will discuss. We will discuss how to actually find the best strategies in those games. And then we'll see that actually this topic is related to linear programming. And you'll see that it actually involves quite a bit of linear programming. It involves formulation of linear programming problems and duality theory. So that's the plan for the next 1 or 2 or maybe even 3 lectures. I hope that we'll have enough time also to have some review before the final exam. I think it will be useful just to go over the different topics and see what kind of problems could appear on the final exams. So I hope we'll have do this as well. Okay, so first of all, what kind of games here we will be talking about? We will talk about two-player games. So two players will be playing some kind of game. A game by definition means, well, a set of rules. And both players are assumed to know what the rules are. We will not talk about if the rules are not clear. We could, but there's less theory about them and much harder. So we'll talk only about games where two players play against each other. They both know what the rules are. They both know what are the conditions for winning. They both know how much they will win once they win, or how much they will lose once they lose. And we will assume that the players are both rational. And when I say rational, I mean some economic theory kind of rationality. It means each one of them cares only about himself, which means he cares only about winning for himself. He does not, if his opponent loses, he doesn't feel dreadful for the opponent, he just wants to win. That's the only desire that he has. And of course, he wants to win as much as possible. If he can win $5, he will prefer this to winning $2. And so let's talk about our first example. Zero-sum two-persons game. It will be example something you're hopefully familiar with. Rock, paper, rock, scissors, paper. So the rules of this game are as follows. Rock meets scissors, scissors meets paper, and paper meets rock. And the way this game is played, well, two players come, they face each other. Each one chooses for himself whether he'll play rock, scissors, or paper. And they both announce their choice simultaneously, so they don't have time to judge what the choice of the other player is. And then they play according to these rules. If both choose the same thing, nobody wins any point. So let's write a table which will list the outcome of the game according to the choices of each one of the players. So each player can choose rock, scissors, paper. Maybe before I continue, is there anyone who has not played this game ever? Okay. So the second player can choose the same options: rock, scissors, or paper. And the outcome is as follows. If both decide to choose the same thing, nobody gets a point. If one of them chooses an object which beats the other object according to these rules, he will get 1 point, and the opponent will lose this 1 point. So rock beats scissors. So if the first player chooses scissors, the second one rock, first player loses, the second player gains 1 point. If the first player chooses paper, it will be beat rock, so I get a win for the first player, a loss for the second one. If the first player chooses rock and the second one chooses scissors, the first player wins. Paper versus scissors, he will lose. Rock versus paper is losing, and scissors versus paper, he wins. So this table summarizes for us, first of all possible choices that each one of the players can make. Each one can make one of the 3 choices, and that's it. You can't decide not to play, you can't decide to choose both rock and scissors. These are the only possible strategies. And this table, well, instead of me explaining to you what the rules of the game are, it explains the rules by itself. It tells, well, for each pair of choices, what is the outcome going to be. So instead of telling you what the game actually is, like explaining what kind of things I expect it to lead to what kind of outcomes, I can just write this one table. And this table is called the playoff table, playoff matrix. And typically, we'll discuss games. Maybe I will tell you some story about the game, some interpretations, so that it will be nicer for us as humans to think about the game. But as far as mathematics is concerned, this is the only data that we need. The possible strategies for the game and the outcomes that using these strategies will lead us. Now I want to discuss a little bit what the word strategy means. When I'm talking about, well, simple games like this, two-person games, like tic-tac-toe is also a two-person game. I put an X, my opponent puts an O, I put another X, he puts another O, and so on and so on. From the point of view of such a table, well, I can specify this game completely by writing some kind of table. Which kind of moves will lead to what kind of outcomes. I cannot write in this table something like 3 X's in one line will lead to a victory. No, I should say that, well, a strategy which is like this. Say, a typical strategy goes like this. First move, put an X over here, and it lists the first move. Then continues. If your player plays such a move, move in such a way. If he plays such a move, play such a move. If he plays, and so on and so on and so on. So the strategy, just one strategy, one row in this table, in this case, should list all possible responses to all possible moves by your opponent. Of course, even in this small game, it will be a tremendous, huge table. It will have, well, kind of 9 factorial 9 times 8 times 7, and so on, rows, it will be huge. So it's really not practical to specify the table by means, the game by means of such a table. It's much easier to specify the game by, well, just in words, saying 3 X's in a row will lead to a victory and so on and so on. It's also much easier to specify what kind of strategy you are using. When I say specify completely the strategy which you are using, it means, let's suppose I want to play this game, but I want to play it remotely. I want to play versus by means of, well, one of you. So I will not be actually making any move, but instead I will, before the game starts, I will explain what my decision process will be. Then I will explain my decision process to one of you, and instead of me playing at this board, I will expect that exactly my decisions, the decisions that I want to make, will be actually made by somebody to whom I explain my strategy. So that's what I mean by strategy. In this case, well, if I tell in the following game I will play rock, well, I know that that's what will happen. I don't have to explain much more. Here I'll have to explain exactly where to put an X after each possible move of my opponent, so it will be much more complicated strategy. And we will discuss only this kind of games. Kind of simple games, and also with some, well, some element of either randomness or, I would say, lack of information. So here, once your opponent makes a move, well, you have some information about what he actually did. Here, the two moves of player 1 and player 2 are announced simultaneously, so one player doesn't have all the information that the second player has at this point of time. So here we have some kind of lack of information. Here we don't. So in this kind of games, tic-tac-toe, say chess, another game which is even, well, much worse than this one in terms of number of strategies. Once again, if you want to specify all possible counter moves to all possible moves, well, with today's computers it's just not possible. So we don't know how to solve chess. And also we will not discuss such things. Maybe to make it even more clear what kind of difference will be between such games and such games. So if in this game you make the rule that the two players make their moves simultaneously, kind of the first one decides where to put the X, the second one decides where to put the O simultaneously, and then they announce their moves simultaneously. And then the rules are, well, if they put their shapes in the same cell, well, they have to decide once again. If not, that's the actual move, and repeat until the game is finished. Well, this puts this game into the category that we will be describing. Something where you don't have complete information about the move of the other player, and, well, some kind of uncertainty, in short. So let me give another very common example that's given in this context. It's called Prisoner's Dilemma. And instead of telling you what the game is, I'll just give you its payoff matrix first. And then we'll discuss the story behind this thing. So there are two strategies called cooperate or defect, and cooperate or defect for the second player as well. And the payoff is -1, -1, 0, -5, -5, 0, -3, -3. So let me discuss this game. First of all, how this game is played. two players, so once again face each other, each one chooses one of the two strategies to cooperate to defect, and the payoff is, let's say, if both choose to cooperate, the payoff is -1 to each one of the two players. If the first player chooses to defect and the second one chooses to cooperate, the payoff to the first player is 0, to the second player it's -5. And similarly for each cell in this table. So the first number in the cell is the payoff to the first player, the second one to the second one. And just looking at this table, it's quite easy to understand what the best strategy in this game is. So what is the best strategy? Well, let's think we are the first player. Should we cooperate or defect? Well, let's see. We can reason about it in this following. The second player is either going to cooperate or he's going to defect. Let's suppose he's going to cooperate. What should we choose in this case? Well, if we cooperate, we'll get -1. If we defect, we'll get 0. So in this case, defect is better. Let's look here. If our opponent chooses to defect and we choose to cooperate, we'll get an outcome of -5. If we choose to defect, we'll get -3. Of course, it's better to defect. So regardless of what the opponent does, our best strategy is to defect. So it's quite easy to understand what player 1 should do. But now this game is quite symmetric. So the player 1 and player 2 have exactly the same choices and exactly the same outcomes. So you can see that the best strategy for player 2 is to defect as well. Once again, you can just repeat the reasoning. If the first player chooses to cooperate, it's better for the second player to defect because he will get 0 instead of -1. And if the first player chooses to defect, it's better for the second player once again to defect because he'll get -3 instead of -5. So once you announce these rules, you know that two rational agents will play according to the following strategy. The first one always defects, the second one always defects. Now I'll tell the story about this kind of game. So it's called Prisoner's Dilemma because of the following story. So the police catches two members of some gang and they separate them in prison. Well, they keep them in two separate cells, they cannot communicate, and they're accused of the same crime, but the police doesn't have enough evidence to actually punish them for this particular crime, so they tell each one the following story. You know what? If you do not confess to doing this crime and you do not tell that the other guy participated in this crime, well, we'll charge you with some smaller crime. You'll get 1 year of imprisonment and the same about your friend. If you choose to tell everything that your friend did, so that your friend did participate in the actual crime, well, we'll release you, but we'll imprison your friend for 5 years. But there is a catch. If we actually propose the same thing to both of you, if both of you choose to betray each other, so if both of you tell that the other guy did the crime, well, we'll give each one of you 3 years of imprisonment. And that's exactly the payoff matrix. And the question is, what is a rational agent to do in this case? And the answer is, never cooperate. It's just worse for you to cooperate regardless of what the choice of the other guy is. So, if the participants in this kind of game are both rational agents, both will defect. And what is kind of hidden behind these words rational agents is, well, first of all, they cannot communicate, they cannot think together about a strategy which will be beneficial for both of them, which is, of course, kind of this one. If you want to maximize their total utility, the utility of the group, of the first one and the second one together, they should, of course, communicate and choose this strategy. But if they cannot communicate and they assure that the other agent will also want the best outcome for himself, well, that's the only possible outcome, -3, -3. Even though it's strictly worse than this one. So these kind of considerations, well, these kind of games, these kind of considerations are at the heart of game theory. So game theory analyzes these kind of games when you don't have, well, at least in our course we'll discuss only games like this. When you play kind of one round of such a game, you don't get to, say, build your reputation of always cooperating or building your reputation of always defecting by playing the game some kind of, I don't know, 1,000 rounds in a row. So just one round of such a game, and we will assume that each one of the players is rational, he is able of reasoning, well, computing, he is able to reason to the end about what the other player will do if I choose to do such a thing, if, and so on and so on. And he only wants the best outcome for himself. Alright, so that was an introduction about what kind of games we are going to discuss. And also we've seen one very simple reasoning, very simple argument, which tells you how to find the actual optimal strategy. So sometimes it is the case that one strategy is strictly better than the other one, like here. For the first player, defecting is strictly better than cooperating in each case, regardless of what the second player does. So what this means is, if you look at the payoffs to the first player, in the second row, they are strictly larger than in the than in the first one. You see 0 is larger than -1, -3 is larger than -5. So this strategy, defect, dominates the cooperation strategy. It's better in each possible strategy for the second player. So let's discuss I'll write a remark about this strategy X. Dominates strategy Y if leads to better outcome for the player regardless of the choice of that one. So in every possible counter move of the other player, the decision X to play X is better than the decision to play Y, like here. And sometimes just this argument, eliminating the strategies which are obviously bad strategies, is enough to analyze some games. So let's see an example. So let's write down our next game. Once again, is a matrix. We have 3 strategies, 1, 2, and 3. And the outcomes are 1, -1, 1, -1, 0, 0. 2 minus 2, 0, 0, 1 minus 1, 4 minus 4, 5 minus 5, minus 1, 1. So here's our new game. Once again, mathematically, this game is completely described. The game is played as follows. Each one of the players chooses one of the three numbers, 1, 2, or 3. They choose the numbers simultaneously, announce them simultaneously, and depending on their choices, these are the outcomes. So if the choices say 2 for the first player and 3 for the second player, the first player gets 5 points, and the second one gets minus 5 points. So that's what the table tells us. It completely specifies what the game is. Well, as usual, it's better to have some kind of nice story about this game. So let's say that this game is about company 1 trying to introduce a new product and to take market share away from company number 2. And they have a choice of their pricing strategy, to price low, price high, price intermediate. And the second company has a choice of its own response strategy, do nothing, or raise their prices, or lower their prices. And in each one of they have to make their decisions. Well, today they don't know what the other company is going to choose. So they have to make the decision before knowing what the other company actually chose. And this is the outcome. So if, say, the first company chooses strategy number 1, and the second company chooses to respond by strategy number 1, the first company chooses, well, I don't know what the units are, let's say 1,000 sales from company number 2. And, well, you see that it seems that this game is kind of rigged against player number 2. I mean, he will lose, the second company will lose some market share in each individual outcome except for this one. Well, so let's see how much is it rigged. So what is the best possible response for company number 2? What is the best possible strategy for company number 1? So let's try to eliminate some strategies which are obviously no good. Let's try to see whether player 1 has some strategies which are obviously no good. Obviously worse than some other strategy. Dominated by some other strategy. Yeah.
So player 1 should not choose 3.
Okay, let's see. Strategy 3, we play with that. And why is it better compared to what other strategy?
Because the maximum player 1 can get is 1.
Okay.
But he can already get 1 from the first strategy if he chooses 1.
So you compare.
So the maximum you can get from choosing 3 is the minimum you can get from choosing 1. If he chooses 1, minimum you can get is 1.
Okay, I see. Yes. So you say that choosing 3 is strictly worse than strategy number 1. In fact, it will be strictly worse. I think the argument is just to make sure that we all understand this kind of argument. Let me change these numbers to this one, so that the argument will not apply. But still, strategy 3 will still take strategy 3 is strictly worse than strategy number 1, even with these numbers. Even though here the worst outcome is 1/2, and here the best outcome is 1. Still, strategy 3 is strictly worse than strategy 1.
because the average you can get is more?
No, it's not about the average. It's about each individual outcome. We know that player 2 will choose some strategy. He will play either 1 or 2 or 3.
Oh.
And the reasoning is, well, suppose that I'm trying to decide between playing 1 or 3. Of course I should choose 1. What is the reason? Well, if I choose, say, 3, and the other guy responds by choosing 1, I'm worse off. I get 0 points instead of 1/2 points. If the other guy chooses 2, I'm still worse off. I get 1 point instead of 2. If the other guy chooses 3, I'm still worse off. Now I lose 1 instead of winning 4. So regardless of the choice of the other player, I will be worse off choosing 3. So strategy number 3 is dominated completely by strategy number 1. Every time you contemplate playing 3, you should instead play 1.
This would have still been the same thing if you left the one.
Yes, it would have been the same thing, just his argument was a little bit more restricted. His argument was that even the worst outcome in strategy 1 is still better than the best outcome in strategy 3. Well, it's not necessary for this thing. It's not, you should not compare the worst outcome with the best outcome in the other strategy. You should just compare the outcomes according to the corresponding responses of the other player. Okay, so strategy 3 for player 1 is dominated by strategy 1. And the reason is, well, 0 is smaller than 1/2, 1 is smaller than 2, and -1 is smaller than 4. Are there any strategies for player 2 which are obviously bad in the same sense? Well, if you look at this table, you'll see that no, there is no one column which is strictly better than the other column. So if you just look here, let's say I want to compare strategy 2 with strategy 3 for the second player. Well, he will be better off choosing 2 if the first player chose 1. He will be better off choosing 2 if the first player chooses 2. But he will be worse off if the first player chooses strategy 3. Because he will lose 1 point in this case and gain 1 point over there. But now he is, well, rational, he is smart. He can compute everything that the first player can. So he knows that the first player is not going to play strategy number 3. Because, well, he knows it's worse to him personally to choose strategy number 3 instead of choosing strategy number 1. So the second player will eliminate this whole third row for himself. So the new table that player 2 now considers after he understands the thought process of the first player is like this. Same thing, but strategy number 3 is never played. So the first player knows that he's not going to play strategy number 3, and because the second player, well, is smart, he can compute, he can reason at least as well as the first one. He also reasons that the first player is not going to use strategy number 3. Okay, but now we do have something which is strictly better for player number 2 than, well, one strategy which is strictly worse than some other strategy. What is this pair of strategies?
Number 3. Player 2 will never play number 3.
Okay, so number 3 is strictly worse than what other strategy? What should be replaced by?
Well, either, right?
Either. Let's see. Yes, either. So strategy number 3 is dominated both by strategy number 1 and by strategy number 2. Okay, so strategy 3. Player 2 is dominated. And now both by strategy 1 and so it's really better for player 2 to choose strategy 3. Okay. Now go to player 1. Maybe player 2 can eliminate some other strategies as well. Well, after he eliminates strategy number 3, strategy 1 and strategy 2, well, if the first player chooses 1, the second player should better play strategy 1. If the second player chooses 2, well, the second player looks like he should play strategy 2. So 1 and 2 are not dominated by each other. They're quite different. Okay, so now both players realized that actually they will face the choice between these two strategies. The second player thinks and doesn't see if strategy which is dominated. What about the first player? Is one of the strategies better for him than the other one?
Always played strategy 1.
I would say
Or
2.
2. No, I was looking at the second.
So strategy 2 is strictly better than strategy 1. Regardless of what the other player chooses, 1 or 2, if the other player chooses 1, he's better off choosing 2 because 1 is greater than 1/2. If the other player chooses 2, well, 5 is greater than 2. So strategy 2 dominates strategy 1 here.
Correct. I think it should be 0, 0 instead of 5.
Oh.
Minus 5.
Sorry, yes, thanks. And does it change? Yes, it does change. Oh. So I did have a reason to have 1 minus 1 over there. Now I realize this. I should have changed it. Okay, so maybe. So in this particular game, there is no strategy which is dominated for either one of the 2 players. And, well, they will have to make their choices, well, somewhat randomly between the 2 things. We'll discuss exactly what kind of randomness they should introduce in this kind of game later. But now, just to make the point, let's go to the original table. And reverse my non-rational decision to change the numbers. So I'll change the outcome to strategy 1 for the choice 1, 1 from 1/2, 1 minus 1/2 to 1 minus 1. So we see that the inequalities that we used previously are not affected. But now we can continue analyzing this game further. So sorry about this change. But now this is the new table for our game. So right here, strategy 1 for player 1 is strictly better than strategy number 2. I mean, if the second player chooses to play 1, there will be any difference between the choices. You will, in both cases, get 1. If the second player chooses to play 2, well, we are not indifferent. We want to play 1. So in either case, we would prefer having chosen 1. So strategy 1, or strategy 2, is dominated by strategy 1. for player 1. Now they are left with even simpler game. We know what the first player is going to play. He's going to play 1. The second player, of course, knows when the first player is going to play 1. And what is his response? Well, of course, to choose strategy number 1, because he loses only 1 instead of losing 2. So strategy 2 is dominated by strategy 1 for player 2. So we get the following answer. Player 1 should use strategy 1. Player 2 should use strategy 1. Player 1 gets 1. Player 2 gets -1 points. So now we see that the best strategy for both players is choosing 1 for the first player, choosing 1 for the second player. In fact, this strategy is so stable that we can even, well, first of all, this game is rigged for the first player. He is guaranteed to get at least 1. If he plays strategy number 1, regardless of the response of the second player, whether the second player is rational or not rational, he will get at least 1. So he will get at least 1. Also, the second player, well, I mean, I don't envy him. He will lose at least 1 point if the first player chooses to play 1, but he can guarantee for himself to lose no more than 1 point by choosing player to play strategy number 1. Moreover, in this particular game, well, we do have some lack of information flow between the two parties. The first player doesn't know what the choice of the second player is going to be. The second player does not know what the choice of the first player is going to be. But on the other hand, even if we change the rules, if the second company sends a spy to the headquarters of the first company, and the night before they announce their respective strategies, the spy tells to the second company, you know what, tomorrow the first company is going to play strategy 1. Well, now we are happy, we have more information, we must be able to play even better. Well, unfortunately, no. You're still going to respond by playing 1 and losing 1 point. So the value of this new information for you is exactly 0. It doesn't matter that you know what the other guy is doing. Well, as long as you are sure that he is rational, you know that he is going to make this choice. Alright, so in some games, just this process of eliminating strategies 1 by 1, eliminating the bad strategies, the ones which are dominated by some other strategies, leads you to complete analysis of the game and to answer the best possible choice for the first player, the best possible choice for the second player. So maybe first any questions about this kind of game? Of course, this game is very, very special. Most games cannot be analyzed that easily. So let's look at some other game which still can be analyzed, but not that easy. So first of all, let me stop writing these pairs of numbers From now on, I'll talk about zero-sum games. Zero-sum games. Games where first player wins whatever the second one, the second player. So in this kind of games, the total amount of the pie that we are sharing is not going to change. Whatever I get, that my opponent will not get. So unlike, say, Prisoner's Dilemma, where we could make the outcome better for both of us by choosing to cooperate, in zero-sum games, we cannot make the outcome better for both of us. If I get something, my opponent will lose something. So, like in this kind of games, if I get 1 point, my opponent loses 1 point. So in zero-sum games, we'll have this property that in each pair, one number is the negative of the other number. So the first number is 1, second one is going to be -1. And for such kind of games, we will not write down the payoff for the second player because it will be implied. We'll only write down what is the payoff for the first player. Only write the payoff sometimes we call the first player the row player and the second player the first player, just according to their position in the matrix. Okay, so let's have another example of the game. The two players are going to choose one of the 3 strategies. And now the numbers are like this: -3, 2, 5, -2, 1, -2, 6, 2, -4. I'll need more space. So therefore. The same example. So, same kind of game, maybe once again about trying to gain share of sales from that company, and 3 strategies. So you can come up with whatever story you have, maybe choosing how to defend the castle, and so how many troops to send out of the army, and this is the number of victims or number of. So you can come up with your own story about this matrix game, but the game is as follows. If, let's say, first player chooses strategy 2 and the second player decides to respond by strategy number 3, the third player gains 2 points. The second player, well, because it's a zero-sum game, loses 2 points. So that's the game, and well, if you look at it, you will study it, you will see, well, there are no strategies which are obviously worse than some other strategies. Neither for player number 1, nor for player number 2. So, well, strategy number 1 and strategy number 3 for player number 1. So, this, depending on the choice of the strategy of player number 2, well, in the first choice for player number 2, strategy 3 is better for player number 1. Here, player number 1 is indifferent, but here he would prefer playing strategy number 1. So it's not true that 1 dominates 3 or 3 dominates 1. You can go like this for each one of the each pair of 2 columns, each pair of 2 rows. Maybe it's instructive to do this for a pair of columns also, because we don't see the numbers in the columns, we see their negatives. So let's compare 1 and 2. Column number 1 and column number 2, strategies for player number 2 for the column player. So if the first player decides to play strategy 1, which of the 2 strategies is better for the column player? One, yes. So in this case, the second player will get 3 points versus getting just 2 points here. So he would prefer using this one. And however, if the first player chooses 1, well, the second player should respond by choosing 2. Because well, here he will lose 2 points, here he will lose only 1 point. So this strategy is preferred. So once again, neither one of them dominates the other. And you can see that in each pair of columns, each pair of rows, there is well, nothing which is obviously worse than something else. So it looks like these considerations are not enough. Okay. Now, recall that in the end of analyzing the previous game, we try to think in the following way. Let's suppose that a spy gets to the headquarters of the first company and well, discovers what the strategy of the first player is going to be. Can he guarantee for himself, even in these really bad circumstances, some kind of payoff? So let's see what he can guarantee for himself. So we'll list for each strategy what is the worst possible outcome. So the outcome which will be achieved if the second player actually knows what we are going to do. If the second player actually happens to choose the strategy which is as bad for us as possible. So if we play 1, the worst possible outcome is us losing 3 points. If we play 2, well, in the worst case scenario, we will gain 1 point. So it doesn't sound that bad. And in case number 3, in the worst case, we'll lose 4 points. So it seems that from the perspective of the worst possible outcome, we should choose strategy number 2. Of course, it does not prove that this is the best possible strategy to play if the second player does not know what strategy you are going to play. Because if for some kind of reason the second player is going to play strategy 3, well, you are still better off choosing 1 instead of 2, because you will get 6 points. Well, except you are not that sure that he will play strategy number 3. He might play as well strategy number 2, in which case, well, you'll kind of be disappointed in your choice and regret that you did not choose strategy number 2. Okay, let's see what the second player can think about his own worst outcome. So the worst outcome is, for each of our choices, we assume that the choice of the other player will be the worst possible for us. So we'll suppose that he actually knows what we are going to choose, and we'll choose the worst possible reply. So let's see what the worst outcome is. If we choose strategy number 1, well, here we'll get 3 points, here we'll lose 2 points, here we'll lose 5 points. So in the worst possible case, we'll lose 5 points. If we follow this strategy, gain of 2, loss of 1, gain of 2, so loss of 1 is, well, the worst possible outcome. Strategy number 3, loss of 6, loss of 2, gain of 4, so loss of 6 is the worst possible. Well, now look. The first player realizes that he can guarantee to win at least 1. The second player realizes that he can guarantee to lose no more than 1 by just playing strategy number 2. But we also know that whatever the first player is going to get will be whatever the second player is going to lose. The overall game is zero-sum. If I get X points, my opponent gets minus X points. So the optimal strategy for both players is to play strategy number 2. Just because, once again, first player knows that he can guarantee for himself a victory of at least 1 point. The second player can prevent the first player from getting more than 1 point, just by choosing strategy number 2. So the first player knows, first of all, I can play to win 1 point, I cannot play to get more than 1 point, because I know that my opponent has a strategy that will prevent me from winning 1 point. The same thing happens for the second player. He knows I can play for a loss of at most 1 point, I cannot do any better, because I know that my opponent, my first player, does have a strategy to win at least 1 point. So each one of the 2 players, by reasoning in this way, understands that he has a strategy which is optimal choice for him. He is guaranteed to win something, and he cannot, by choice of any other strategy, guarantee for himself a better victory. So this game is still rigged for player number 2, it's still number 1, it's still not fair. Player number 1 will still win 1, player number 2 will lose 1, but still it is the best outcome for both in this kind of game. So let me write this down. Player 1 can guarantee to himself a victory of win at least 1 point. And the second player can guarantee the first player wins no more than 1 point. And the playing so strategy 2 for both players is the optimal strategy. So for some kind of games, we'll analyze in a second what kind of property we used throughout this game. But for some kind of games, this kind of reasoning, even though we cannot simplify this game, we cannot eliminate strategies which are obviously bad. Still, we can guarantee that one of the strategies is the optimal for one of the players, and one response is the optimal response for the other player. And what we have is a notion of kind of security level. If first player uses strategy to secure for himself a win of at least X points, and the second player can achieve for himself a security level, which means he will know that his opponent will not get more than X points, then we know what is the optimal response for, what is the optimal strategy for player 1, what is the optimal strategy for player number 2. So let's formalize this a little bit. I'm talking about this security level thing. We'll start moving towards analyzing most general possible matrix games. So in a matrix game, by matrix game I mean just two-player zero-sum games given by such a matrix. The matrix A and J, which means A11, A12, A21, and so on. So if I'm given a game with this matrix of outcomes, the security level for player number 1, and I will have to add some adjective here, pure strategy. I will explain later why I need to add this adjective, pure strategy, security level. But for now, let's just talk about the security level for player 1 is, first of all, I'll explain what is the meaning, is the game player 1 can guarantee himself by the choice of one of the strategies. So he can guarantee for himself to get at least X points. And what this X is? Well, this X is in each. So how did we go about finding the security level for player number 1 over there? We went over each one of the rows. In which one of the rows we chose the worst possible outcome for him. So we went over each row. Let's say row number I. We looked at numbers A and J. Among those, we chose the smallest number. We went over all possible indices J in the row. We chose the smallest possible number. This is the numbers in the right column. And now among all possible strategies, we choose the one that guarantees the largest gain. So among all these numbers, we choose the largest. So mathematically, well, a way to compute this security level for player number 1, how many points he is guaranteed to win, is this thing. We go over all rows. In each row, we choose the smallest number. And among this list of smallest numbers in each one of the rows, we choose the largest one. Well, we can talk about the similar thing for the second player. So we'll talk about security level for the second player. Security level player 2 is the number x something layer 2 I can guarantee layer number 1 you gain no more than x. So once again we'll talk about the gain of player number 1, even though we talk about the security level for player number 2. So now we'll talk about, just because we know that one is the opposite of the other, we know that the gain of player 1 is the loss of player number 2, so it doesn't matter which one we are talking about. So in this case, security level for player number 2 is the number of points that he can guarantee by choosing by choice of one of the strategies for himself. He can prevent the other player from getting more than X point. So like here, like in the game that we just discussed, if the second player chooses to play strategy 2, he knows that the first player will not gain more than 1 point. So that's his security level. And mathematically, well, what we are going to do to find out, well, we go over all the columns. So once again, we look at numbers in the table. Now we'll go over columns, which means we'll change the index I. In each column, we'll find what is the worst outcome for the second player, or in other words, what is the best outcome for the first player. So you'll find the largest number in each one of the columns. And then we'll choose the column for which the outcome for the first player is the worst. So talk about the minimum in this list of numbers of the smallest number. So that's the security level of player number 2. In general, we know that these numbers might be different. You see, well, first of all, these expressions, they look kind of similar, max, min, max, something like this, but they are different. I mean, here we go over rows first, then over columns. Here we do the opposite way. Here we minimize first, then maximize. Here we maximize first, then minimize. So these numbers are different. In some games, when the two security levels coincide, well, then you know that you are done. So if security level for player 1 is the same as security level for player 2, both should pursue their security strategies. So if you know that the first player can guarantee for himself a win of X points, and the second one can prevent him from a win of more than X points, well, we know what is the optimal strategy. First player should guarantee for himself this win of X point. The second player should try to prevent him from getting more than X points. And each one knows that he cannot do any better, just because of this thing. Of course, it's not the case that this is true for any kind of game. In fact, today we already talked about a game where there are both no dominated strategies and this thing is actually wrong. Does anyone remember a game that we had where we had no dominated strategies and the security levels for the two players were quite different? So maybe before this, is the concept of security level clear? Is it clear why if the security levels coincide, then we do have some optimal strategies both for player 1 and player 2? Good. So now try to come up with an example of a game. In fact, we mentioned one game today where the security levels for the two players are different. There are no dominated strategies. Well, and for now that's it. So, and hence we cannot analyze it completely yet, and still you all know how to play it. Yeah?
Rock, paper, scissors.
Yes, exactly. So let's go back to rock, paper, scissors. So rock, paper, scissors. Rock, paper, scissors. The outcomes, well, rock versus rock is 0, paper versus rock is a win, scissors versus rock is a loss, rock versus paper is loss, paper versus paper is tie, scissors versus paper is a win, rock versus scissors win, paper, scissors, loss, scissors, scissors, tie. So first of all, obviously no strategy is strictly worse than any other. So you know this. Another thing, what are the security levels? So security levels. Layer 1. How many points he can win assuredly? Well, in the worst case, for him, each one of the 3 rolls is -1. So if the second player knows what the choice of the first player is, he can make him lose 1 point, of course. So the security level here is -1. What about player number 2? Well, the security level for player number 2 is what you can, is if you place in such a way as to guarantee for the first player the smallest possible win, what you can do? Well, the answer is he cannot guarantee any win smaller than 1. I mean, whatever strategy he chooses, the first player has some possibility of playing in such a way as to gain 1 point. So the security level for player number 2 is 1. I mean, he can prevent the first player from getting more than 1 point, but he cannot prevent him from getting, say, 0 points. From more than 0 points. He cannot make the first player win 0 points. So the security levels here are quite different. So we don't have, well, some kind of agreement like this, where we can say that the first player should play paper, and the second player should play scissors, or paper, whatever. No, whatever the choice of the first player is, the second player might be able to come up with some strategy which will do better. I mean, to make the first player lose something. Okay. And yet, we do know how to play this game. What is the usual strategy for playing this game? Well, the answer is choose randomly. So choose in such a way that your opponent will not know what your choice is. So if for some reason you only play rook always, well, you're doomed. But if somehow you randomize between choice of rock, paper, or scissors at each move, well, you do have some kind of expected win. And usually it is 0. So over long term, you'll get exactly 0 points. So just an announcement for next time. We'll discuss this kind of actually interesting games, where there is no strategy which is actually optimal, where you do have to randomize. And we'll discuss exactly in what way to randomize. So see you next time.
Yeah, it did. Yeah, I think maybe the example. Yes. Maybe you got the example again. I don't know.